Our next speaker is Yunqing Tang from Princeton University, who's going to be talking to us about the unbounded denominators conjecture.
Thank you very much for the introduction. It's my great pleasure to give a talk at the summer school. The conference of the summer school. It's like the Connecticut summer school. It's a very nice one being there once, like in person. Okay, so today I'm going to talk about the joint work with Frank Karagari and Vasilin Dimitrov about unbounded denominator conjectures, and also I'll mention a key ingredient in the proof, which also have other applications. Let me start it to talk a little bit about the background of the unbounded denominator conjecture for modular forms. So essentially the topic is about down to earth speaking is finite index subgroups of SL to Z. And so there's a very special type of subgroup, so-called the principal congruence subgroup, namely those ones congruence to the identity matrix modulo N. And thus we can distinguish the two type of finite index subgroups. One is the so-called congruence one, namely is those ones defined by some congruence condition. In other words, it contains gamma n for some n, and also the non-congruence ones, namely that those ones are not defined using congruence conditions. And so most of the finite index subgroups of SL to Z are actually non-congruence, while for groups of larger rank, so say SL and Z when n is at least 3, or SP2 and when n is at least 2, they are actually congruence. So this is a classical work of Bas-Lazar's theorem and also independently by Minnick. So which means today's topic, since we're talking about two different types of subgroup of SL to N, so we'll restrict our story to module forms of SL2 and also elliptic curve. So what we're going to talk about doesn't have the natural generalization to say abelian varieties. So we focus on the simple group SL to Z. Okay, so we have these two type of groups, and let's just see what's the situation when we kind of modulo out these groups and study modular curves associated to the groups. Okay, so we have the above plane with the action of SL to Z. We quotient out the finite index subgroup that gives us modular curves. They have natural complexifications, and by adding the cusps. And here are two kind of familiar examples of groups of SL to Z, say SL to Z itself, and also gamma 2, namely the ones which congruence to 1 mod 2. And for these, we can study the modular curve, and in both cases, they are essentially just the projective line genus 0 minus a couple of points. And so which means it has a coordinate. And in the SL2Z case, we just have the J function, which is the J function of elliptic curves. And when we deal with gamma 2, we have the following modulo lambda function, which can be defined using the following formal product. Okay, so the formula doesn't really matter for today's talk, but what is important is when we look at the Q expansion of the J function, it has Z coefficient. Sorry, there's a typo. It's I should have put a Q inverse here. And also for the lambda function, we see that it's actually Z coefficients in terms of the Q expansion. So is this always true when we kind of talking about module forms or module functions? Let's just look at the following example. Is that so there's a nature n's power maps, just x maps to x to the n on C, and hence it's instead of just looking at gamma 2, which is we normalize this so that C minus 0 and 1 over 16, we can take n's roots. And since this is a covering map, so it naturally gives us an index n subgroup inside gamma 2 induced by this covering map. And then the modular curve is just you take the pre-image of these two cusps. So it's, pre-image of 3 cusps 0, 1 over 16, and infinity, take the nth roots of it. So these are the cusps, so C minus these ones. And so it also has a coordinate, and the coordinate is nothing but just the lambda taking the nth roots. So we know that when we have a power series like x plus, sorry, here is like q plus like high powers of q, we take the nth root, then it's still a power series like with q coefficients in q to the 1 over n. So actually, it's like it is a very classical result of Klein and written in a lecture notes written by Klein and Frick, is that this group is congruence, is defined by congruence conditions if and only if that the n here divides 8. So one can explicitly do a computation to determine this fact, or alternatively, one can have the following observation. So what matters for us is like, let's just look at the formula, the definition formula of lambda here. We see it's like, if we take the 8th root, it still have z coefficients. But if we take some roots which is like, doesn't divide 8, then like, for instance, we take the 3rd root, that we can actually explicitly compute the Fourier coefficients, and we see that the denominators show up, so you have like 3 show up on the denominators of coefficients, so it's no longer z coefficients. And what's more is like one can actually like looking at the valuations and see that actually the denominator is getting larger and larger. So in other words, it's like there's just not a common kind of there's no kind of finite common denominators for all the Fourier coefficients. And this is actually indeed goes back to the work of Atkin and Schröter when they proposed that this is like one way to distinguish like congruence versus non-congruence subgroup. So it's like, let's just look at like two things that I just, two facts that I just told you without proofs. It's like, in this example of this gamma lower n, it's congruence if and only if n divides 8. And if we look at the Fourier coefficient of this coordinate, and it have like so-called unbounded denominator, because denominator gets larger and larger, you can actually try using like your favorite like computational tool that like it's the denominator is unbounded like as far as like n doesn't divide 8. So that was actually the conjecture proposed by like Atkin and Schröter, and that's the first result that I would like to present today. Instead of, so I think the idea is just like saying that we can actually look at the Fourier coefficients of module forms in order to distinguish congruence and non-congruence subgroups. So this is kind of a vague statement, and now I would like to actually give the precise statements of the theorem. So in this talk, by a module form of weight k and the level gamma is like it has this like transition law with respect to gamma, but we allow it to be meromorphic at all the cusps. And by the Q expansion is that we can always like pick a cusp, and in the end of the day, it doesn't matter which cusp that we pick. The whole statement will still hold true, but for simplicity in this talk, we'll just pick the cusp I infinity, and then we can write the module form in terms of Q expansion. And also for simplicity, we'll assume that it's holomorphic at this cusp. And the precise, So when we talk about module forms and Fourier coefficients, these like numbers are in C. And the previous examples that I've shown are like talking about module form with coefficients inside Q. So this is actually, we do not lose much in this situation because that, so first is like all the module curves are defined over Q bar because it's a like ramified cover at 3 points, which are like 0, 17, 28, and infinity to the J line, and that's why like there always has a model defined over Q bar. And also the vector space of module forms is also like spanned by module forms with Fourier coefficients inside Q bar. So for today's talk, and actually for the previous like conjecture of Atkin and Schröter when they talk about like distinguish module congruence versus non-congruence subgroups using module forms, we focus on module forms whose Fourier coefficients lies in Q bar. And then when we talk about Q bar, denominator versus no denominator is like just a no denominator means it's an algebraic integer. And the precise statement of the theorem is following is that when we look at a module form and with Q expansion inside Q bar, and the following two are equivalent, is like the first statement just says when we look at its Q expansion, it has bounded denominator, namely that the integer n kills all the denominators. And this is equivalent to say that the level of f, namely just the largest gamma such that the transition law for the module form satisfies, is actually congruence. So that's why in the previous example, when we look at like genus zero module curve, so we have like a Hapton modulo the coordinate, so that's the actually module functions that we study to see whether like the finite index of group gamma is congruent or not. So two parts, so we said that these two things are if and only if. So the more classical part is that 2 implies 1. That is essentially the Heck theory. So one can actually first reduce the question to all the like module forms which are homomorphic at all the cusps. And then now we are in a good shape to apply the Heck theory for module form, saying that every module form can be written as a finite linear combinations of normalized Heck eigenforms. And then the theory for like Fourier coefficients of Heck eigenforms related to like forbiddance action on certain like L-adic Galois representations knows that like all the Fourier coefficients for the Heck eigenforms are algebraic integers. So that's why like the 2 implies 1 part is the more classical part, which you can find almost surely in like many textbooks in module forms. And the relatively new part is the part that 1 implies 2. That is the joint work of Frank Calgary, Valentin Dmitriev, and myself, that we prove that if we know that the Fourier coefficients of a module form doesn't have like, has bounded denominator, then it must be congruence. So this is actually the first results that I would like to present before I move on to talk about the idea of proof and what is one of the key ingredients. Is there any questions?
Check the room. Questions? No, not at this time.
Thank you. Okay, so let me just summarize what happened is we study finite index subgroups of SL2Z, and then we have 2 types, congruence and non-congruence. And what we just said is we can use Fourier coefficients of module form to distinguish these 2. Okay, here's the idea of proof. It's standard to reduce the theorem to the with 0 module form case. And then we fix a number n, where n is the least common multiple of all the cusp widths of gamma. So namely, it's you look at Fourier coefficients, you look at the Fourier expansion at all the cusps and write it into q. You can always write it into q to the 1 over n. Okay, so we have 1 and 2. We can count actually the dimension of the vector space spanned by function module forms in 1 or 2 over q bar lambda. So first thing is let's just talk about the 2 part, because the 2 part is more classical, is that why is it finite dimension and what's the dimension? So it's a result of Wolfach. That's why the n here is actually called Wolfach level, is that all these weight 0 they are first kind of meromorphic functions on certain module curves, h quotient of gamma. But here, this Wolfach said is if we know the LCM of the cusp width, then we know that the smallest congruence. So what is 2? 2 are module forms which defined over a congruence subgroup. So all the congruence subgroup, everything defined by certain congruence conditions, such that the cusp width, all the cusp width divides n, must contain gamma n. So gamma n is the smallest one for this this Wolfach level. So which means that all these module forms are meromorphic functions over h star over gamma n. And then, sorry, I forgot to fix the typo here. So that's why the dimension of the functions over q bar lambda will be the index. Sorry, I should have switched these two. The index of gamma n inside. Sorry, there. Okay. If we talk about, so here's like a couple of like vague things which doesn't matter for us. The first is like if we deal with it over lambda, then I should have like put a gamma 2 here, but like since this is called up to a constant, so doesn't matter. So up to the constant is the index of the group gamma n. And what is the index? We can actually there's a concrete formula. The index is roughly n cubed. Okay, so this is the asymptotic as n goes to infinity of the dimension for 2, namely it's like congruence module forms. So what happens to 1? So that's like one of the key ingredients is like we're going to introduce one way to actually bound the dimension of like the vector space spanned by module forms in 1, namely that those with like bounded denominators. And so it has 2 steps. It's like I'm going to present so-called our refinement for Andrews algebraic criterion, which will give us a dimension bound formula. And in order to actually compute the formula, one can explicitly compute something and so-called conformal radii and the nonlinear theory to get this bound. Okay, so here there's nothing that we can say right now because it's like we can at least see everything match up because it's like as I explained that everything 2 is an element inside 1. So of course the dimension for 2 is no greater than the dimension for 1. And we want to prove the dimension are the same. So we have two vector space, one sits in the other. And to prove they're the same, we need to prove the dimension are the same. But unfortunately, like these are all like first like up to constants. So these bounds are up to constants. How are we going to conclude? So we conclude by saying that if the difference is at most log n, then there should be no difference. So that comes from that if there's one counterexample, namely an element which is in 1 but not 2, and then one can construct another element with a slightly different level, and then these two things are actually quite independent. So they add new dimensions to the vector space of dimension 1 as like we take more and more prime numbers. And then we can conclude that this is not going to happen. It's like one counterexample will lead to too many counterexamples which violate this only extra log n bound. So in the end of the day, we conclude there should be no counterexamples. So let me just summarize. It's like we fix an n, we try to count the dimension. As far as we have a reasonable upper bound for the dimension of module forms with bounded denominator, we can finish the proof. Okay, so now the question is like, how are we going to give an upper bound of the dimension? So I would like to go back to something which is like more elementary. Okay, so first thing is like, let's look at let's look at the power series with z coefficients. And then what can we say about the power series is that if the convergence radius of the function is strictly greater than 1, then it is a polynomial. So that's a quick exercise of calculus. And one can upgrade it, namely it's like one can make it more adelic. Instead of saying that the Archimedean place is a special place, we can just talk about the convergence radius at all the like places, no matter it's like non-Archimedean or Archimedean, then take the product of all. And moreover, to refer to something in the literature is like in the work of broad work, actually like when the work trying to prove the rationality of the zeta functions, we can actually study the convergence radius of meromorphy and then get a similar formula criterion. Okay. So, but so far this is not good enough for us as I'm going to explain later. But one thing we could do is that instead of, so previously we're talking about convergence radius. So, and now we just make something which is weaker than the convergence radius. Namely, it's like we look for a homomorphic map from the unit disk to C, 0 tends to 0, such that the derivative is greater than 1. And we hope that f composed with phi, or f pullback by phi, is meromorphic on the disk. And then it is a theorem of Yunqing saying that this is actually, so previously, if we talk about the convergence radius, we conclude that it's a polynomial. In broader work, when we talk about the radius of meromorphy, we conclude it's rational. And here we no longer just talk about like disks around 0. We just talking about any maps from a disk to C. And then our conclusion is like this power series is actually the Taylor expansion of some algebraic functions over Qx. And so you can do an adelic version. And if you just do kind of like scaling of disk, that recovers the previous broader work. And moreover, what is more important is like the proof is actually effective. It gives an upper bound of the algebraicity degree. And now let's just go back to the module form situation. Is that, okay, so we, for simplicity, let's just talking about like module forms like with z coefficients. Okay, so the core is like we have lambda over 16, which is like q plus like high powers. And this says that actually, if we take x to be lambda over 16, things like q can be written as x plus like high power in z coefficients. So we know that our function f, if we view it as a power series in x, is actually also has z coefficients. Okay, so that's how it is related to our previous thing. And then, so a priori, we know that it's a rational function and the curve which admits a finite ramified curve to the lambda line, and hence it's algebraic over q lambda. And then once we could find a suitable phi in Andrews' theorem, we'll be able to give an upper bound of the algebraicity degree, which is closely related to the dimension. Why? Because it's like, when we're talking about algebraic degree, it's essentially saying it's like it's the dimension of the vector space spanned by 1 f squared powers of f. So these are all like meromorphic functions with like the same like properties as before. So that's why the algebraic degree, like in the proof, will actually help us to get the dimension bound. And this is what we have. So let me actually first present the bound and explain things. Okay, so it looks a little bit complicated. The reason is like when we have the cusp width, which is n, we no longer work with q, we work with q to the 1 over n. And the correct coordinate to work with is not lambda over 16, but instead we take the nth root of like lambda over 16. And the function phi is going, sorry, let me just mention that there is a good choice of the function phi for the following reason. Okay, so it's like the z coefficients part is the z coefficients part related to the z Fourier coefficients. And then, so the phi is still, is like, so we have record the criterion of NJ saying that we have a power series z coefficients and we have a map phi such that its pullback is like meromorphic, and then we're going to give a bound of the dimension. So the dimension bound for all these functions, so the e part you could ignore, it doesn't play a role in the later part of the proof, is that it's related to the function phi. And so the reason that we want the derivative to be at 0 to be strictly greater than 1 is so that like the denominator is actually a positive number. Okay, so the upshot is like Andrews' criterion says that if we have a phi, we know the function is algebraic, and here we can actually give a dimension bound explicitly in terms of the function phi. And then the choice of the function phi is the following: is like if we look at the formula, it's like we want the value of the function is to be not too big. That's the numerator, the log plus of the integration, the integration of log plus. And we want the denominator to be large. So we want a function such that it's kind of like a homomorphic function, such that like the denominator is large. And but still kind of having the convergence things. And since we have a module form, so we want to like the Fourier expansion of the module form at the cusp, we want to avoid all the other cusps. So that's why we want to avoid all the like nth roots of like 1/16, but we still want the derivative to be as large as possible. So that's why we'll take phi to be just the like essentially the universal cover. And then like since we want a closed disk, we just shrink it a little bit so that the integration here is not too big. So the upshot is like, okay, so let me actually talk back to the application of the unbounded denominator conjecture to say what's the upshot of the theorem. It's like you can take the z version or the z bar version, and then we have that we want a dimension of the upper bound of the space spanned by module forms with like z coefficients. And the z coefficient parts satisfy the condition 1 in the theorem. And then the level, the Wolfart level at n will imply the second part of the theorem. That is like the specific choice of our like function phi. The specific choice of our function phi will guarantee that like when we pull back our module forms into that disk, it will still remain to be homomorphic, actually meromorphic function, so that we can actually apply our criterion to get a bound. So the bound is like we take the universal covering, we shrink it a little bit. By a little bit is like we take the radius to be roughly like n to the -3, and then one can explicitly compute like both the conformal radius, which is like another way to say the derivative of phi at 0, and also kind of the numerator. The numerator is actually the Navier character, so one can actually compute like by compute, I mean, give a good bound for both of them like asymptotically with respect to n and get the n cubed log n bound. So okay, so let me just make an extra remark is that so in the previous formula, let me go back to the previous. In the previous formula, this constant e doesn't matter because in the end of the day, we just want up to a constant asymptotic bound. So the e doesn't matter. In real work of Boss and Schatz, they can improve the like bound from e to 2. We could also give an alternative proof. Inspired from their work, we can also give an alternative proof using different methods to get the same kind of like bound with the the leading coefficient to be 2, because I would like to give another example which indicates in some cases we do care about like what exact number it is instead of just the asymptotic. So before I move on to the another application, any questions about the unbounded denominator conjecture?
I'll check the room. Yes, there is a question.
So in your proof, you made an essential use of this function lambda over 16, and you said that there's alternate, well, you say alternate proofs. Is that alternate proofs of just the dimension bound or of the
dimension bound? So this
Okay,
remark is only about dimension bound. Yeah.
So at present, the only proof makes essential use of this function lambda over 16?
So here's two parts of story is that, so this theorem here, this bound doesn't matter which one that you use.
Yeah.
So it's just a formulae thing about like you have a power series with z coefficients, you pull back by a function such that it's holomorphic, and then you have this dimension bound. This has nothing to do with you take lambda or other functions that you want.
Yeah.
And this can be improved. So we have actually in our paper, there's already like more than one proof of this dimension bound. So there's many proofs, and this is actually not even the optimal version that we could prove related to these type of things. And so this itself has a proof which has nothing to do with the lambda function. The lambda function is going to, let me put it this way, and the lambda function is not what we are going to pick for the function phi here. It is related, but it's not the same thing. So actually, let me just take this opportunity to remark. It's like, as we said, it's like the lambda function is used to give the coordinates here, but the phi function is actually not just like take the disk here is not the q disk, because it's like if you do the q disk, you do the lambda function, like the pre-image of 0 is unique. And here is like we take a universal cover. So here, like we remove the 0 and we take the universal cover. So like the pre-image of 0 here is like infinity many. And the reason for that is like that is the part that I did not explain in details, is like the Wolfram level, the cusp width guarantees that once we take the nth roots, once we take the coordinate, the nth roots, then like there's no local monodromy around kind of all the cusps. When we kind of like do this like universal covering, so that we can actually like see all the modular functions, not modular forms. We're talking about modular functions. So they are actually like rational functions on a covering to like the lambda line with like local monodromy to have like finite order divides n. So that's why like one can actually pass to the universal cover here.
Okay. All right. Thank you.
Any other questions? That's it for now.
Thank you. Okay, so now let me present another application. Let me talk about the application first and then talk about why it is also related to the previous thing. So the application is about like zeta values. So we have the Riemann zeta function, and the conjecturally at the 4-o'clock conjecture that all the zeta values are like algebraically independent. But the results, there are many results on like the dimensions spanned by like various like zeta values. But if we restrict ourselves to just the one zeta value, and that's essentially what we know. We know that zeta 2 is not algebraic, and we know zeta 3 is not rational. Okay, but I won't be able to say more about kind of zeta value, the classical zeta value, but we could work with the periodic one. And so here is like one way to define like the so-called periodic zeta value. And as essentially as a limit of the zeta values when we take elements getting close to k. So that's kind of one way, like using like interpretations when define periodic things. Or in other words, one can also like define like so-called periodic Eisenstein series, and things like zeta values show up as the constant term of Eisenstein series. So these are also like show up in the constant term of like periodic Eisenstein series. And in early work of like Frank Carragari, he proved that like these two zeta values are irrational. So like when we do the like periodic limit, we know that it lies in QP, but if one kind of compare the periodic and the classical world, one probably say, we expect that all these periodic zeta values also to be irrational. And so a theorem that we could prove using like the ingredients of the another dimension, a similar dimension bound is that we can prove that the triadic zeta value at 5 is not rational. Okay, so I would like to say a little bit about like how is like this result related to like the previous thing. So the setup is following, we actually following the work of Frank, is that, as I said, the periodic zeta value show up in the constant of certain like periodic, like Eisenstein series. And then we pick, so it's weight negative 2k. So we pick a weight 2k classical Eisenstein series and take the product. The product is weight 0. And in this case, both of them are defined over x naught 2. So this is also kind of like a genus 0 modular curve. So we have a coordinate, and the coordinate is also very nice. It's kind of like has like q plus q squared with z coefficients. So we can actually write our like weight 0 module form. This is a periodic one as a formal power series in terms of like this Hopton modulo. Okay, so now we have like some periodic module forms that we would like to study. And one thing that we see from the previous one is that, let's just talk about the broad work, is like when we have a power series with like q coefficients, we study its convergence radius at all the places, and we have a dimension bound which essentially depends on like the convergence radius. And if we want to kind of do something more general, we'll get some like constants related to the uniformization. So let me just look at what do we have in this case. So in this case, it's like these are the observations that one can make about the denominators, and hence one can conclude that as a module, as a power series in X, this one has like convergence radius at least 1 for all the primes. And then using some input from periodic over convergence module forms, one can conclude that at 2, the convergence radius is pretty big. That's good. And then also at infinity, if we allow ourselves to just take a map from the unit disk to the coordinate such that the pullback is convergent, then we can actually take the Q expansion. So like we're in a pretty good shape that we have like all the convergence radius to be not too small, and we also have like we know concretely what they are. Okay, but like the key difference is like in the previous situation we have like z coefficients power series, or z like with like 1 over n inverted. In this case, we only have something with q coefficients, and all the, if you just look at the denominator, all the primes actually show up in the denominator. And that's why we won't have something as simple as the baby version that we've seen before about something being a polynomial. So let me actually just give the conclusion. So the conclusion is that if we have a power series, previously we said if the product of the convergence radius is greater than 1, then it is polynomial. But if we have like so many primes in the denominator, we need to introduce a constant. It's denoted by the tau invariant in Andre's work, and which essentially coming from, if you think about the proof of the baby case, is that essentially coming from just we need to exchange to limit, and then when we only have finitely many primes in the denominator, we can exchange the limit with no problem. But like in general, we cannot, so that gives an extra term. But a natural generalization would be just now let me just take log. It's like if the summation of the log of the convergence radius is greater than this tau invariant, then it is a polynomial. So the generalization of Andre's theorem is that, so now it's like we have linear combinations with tau invariant smaller than sigma. So in the previous case, sigma is 0. And then we have some periodic convergence radius. We also have a function such that when we pull back, it's homomorphic. And then, so instead of previously we say that the log of derivative plus the radius greater than 0, now it's like greater than sigma. And then the Q vector space spanned by these functions is given by this formula. So like in the previous theorem that we've seen was the special case when all the RPs equals to 1 and the sigma equals to 0. But the difference is like here we use the sup bound and previously we use the integral bound. That's why I said like there are different versions of the dimension bound, and there are a more general version which kind of uniformize these two statements, which we can prove using the slope method, but let me not give that technical statement. Okay. So now we can actually apply to the zeta to 5. So let's just recall, it's like we have our periodic isonstat series. Since we want to zeta to 5, so we get a negative weight 4 periodic isonstat series, pair it with a weight 4 classical isonstat series. We look at this function. And then, so we can actually compute that the sigma in this case equals to 5. This is just an easy application of the prime number theorem. And the one thing is like, although that it's slightly different than the previous algebraic criterion that I said you could get the algebraic degree by looking at the function 1f squared powers of f. But here we cannot take powers of the function because if you have something with denominator, you take the power, the denominator will get larger. But one thing which will not increase the denominator is by taking the derivatives. And also it doesn't change the convergence property. So we can take functions which not just this one, but we can take derivative of it. So the sigma will still remain the same. Sigma is still 5. And then phi is essentially the Q expansion. But like we will not just take the entire Q expansion, although it gives us a pretty large denominator, but like the numerator will also be super large if we take the entire like disk. So basically, essentially what we do is like you look at the Q expansion disk, you choose some small region inside it, so that kind of the soup of this like the soup of the value of the Hobson modulo is not too bad, and then one can actually make a good choice so that the entire dimension bound is strictly smaller than 6. And then the contradiction follows from is like, one thing that, sorry, I forgot to mention is like, when I say that we can take fi to be this function, that was under the assumption that assume for contradiction that the two-adic zeta value is rational. So, okay. So let me just go back a little bit. It's like, this is the thing. And assume for contradiction, this is rational, then we can conclude this has rational coefficients. I mean, if this is irrational, then we, like all the rest, just like we no longer have rational coefficients. So that's where the first assume for contradiction. So assume for contradiction that all these ones has rational coefficients, which is the same as assuming that the two-adic zeta value at 5 is rational. Then we have like function 1 f derivative of f and up to 4th derivative. The 4 is related to the weight here, as one can prove that like all these functions are linearly independent. And so this would contradict with our dimension bound. So which says is like our first assumption saying that the two-adic zeta value at 5 is rational so that we can construct so many functions with such good properties is just not valid. And hence we prove by contradiction saying that the two-adic zeta value is irrational. And that's it. Thank you very much.